Section 4.8, Newton's method. This new method is helpful when trying to find zeros of a function. So to derive Newton's method, we work with our derivative and we find the slope using the derivative. And then along with our point slope formula, we have the idea of what would come to be our Newton's formula. We go ahead and we set it equal to 0 and solve for x, and call x sub n plus 1 to come up with this new method. So this is Newton's method for approximating roots of f of x equal to 0. So your steps are, you want to choose an initial approximation for x sub 0, and that's just a point that's close to the root. So for any n from 0, 1, 2, and so forth, our rule is x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime sub x sub n, provided that the derivative is not 0. You end the calculations when the termination condition is met, meaning you get the same result over and over again. Let's do this by an example. Approximate the roots. F of x equals x cubed minus 5x plus 1 using 7 steps of Newton's method. Use x naught equals -3, x naught equals 1, and x naught equals 4 as initial approximations. So if we look at our picture of our function, we see that we have a 0 here, here, here. And those are not integer solutions. They're decimals, and we're not too sure what those decimals are. We're going to proceed by using Newton's method. Now, for the first one, we're testing -3. And we're just choosing a point that's sort of close to our 0. Then we're choosing 1. And then we're choosing 4, which isn't close at all to that other 0. But we'll see that by using Newton's method, it gives us a value that will approach that 0. Okay, so let's go ahead and list out these steps. As we look at our formula, we see we need some value xn, our original function, and the derivative. So let's begin by finding our derivative. Find a f prime of x. So our derivative f prime of x is equal to 3x squared minus 5x, and that comes from our function f. And I made a mistake already. Just 5, not 5x. Okay. Next, we want to consider the formula. So your formula states x sub n minus f of xn divided by f prime x sub n. Okay, so we're going to create this equation using our function f and our derivative of our function f, so that we have xn minus our original function, which is x cubed, minus 5x plus 1 divided by our derivative, which was 3x squared minus 5. And I forgot those little n's, so let's go ahead and write them in. Okay, now for the sake of always working with that same equation, that comes from our formula, let's go ahead and clean it up. So let's go ahead and simplify. All right, so we need to go ahead and multiply the denominator to that first one, so that we get 3xn squared minus 5 times x sub n minus x sub n cubed minus 5x sub n plus 1 all over 3x n squared minus 5. Okay, and all we're doing here is clean it up. right? So we distribute that xn, distribute that negative, all right, so we're left with negative 3xn cubed minus 5xn minus xn cubed plus 5xn minus 1 all over 3xn squared minus 5. And we clean it up, right? So here we can combine like terms for those x cubes, and we're left with 2xn cubed plus 1 divided by 3xn squared minus 5. And this is going to be our formula. Now, what is Newton's method? We're going to evaluate for a value each time. Now, according to our question, it wants us to start off with negative 3. Let's go ahead and start off with negative 3. So let's go ahead and evaluate for negative 3. So I have 2 times negative 3 cubed plus 1 divided by 3 times negative 3 squared minus 5. And use this first one isn't so bad, but for the rest, you'll use your calculator for sure. So make sure you have your calculator handy. For this one, we get negative 2.5. Now we're going to go ahead and repeat that same formula with this new answer. So we have 2 times negative 2.5 cubed plus 1 divided by 3 times negative 2.5 squared minus 5. And you for sure need your calculator for this one. Your answer will be negative 2.345455. And yeah, have your calculator handy, pause the video so you can give it a try yourself. Now let's go ahead and plug it in again to a new function. Same formula, different substitution. So I have 2 times negative 2.345455 cubed plus 1 divided by 3 times negative 2.345455 cubed minus 5. And this time we get negative 2.33023. And you're going to keep continuing. Are you starting to notice a trend? Well, maybe not so much yet, but it's getting close to 2.3, and as we plug in more values, it becomes more precise. Now here I have a chart from the textbook. So you see we started off with 3. This was our first answer, our third answer, our fourth answer, and if we continue, we're going to get a closer and closer answer. So we can say that the 0, that first 0, is negative 2.33059. That's that first 0. Now it wants us to repeat the same process with 1, 4, 1, and 4. So we go ahead, start from here, and start with x0 is, we said 4, or we said 1. 1. So we go ahead and continue using that same formula that we got from Newton's method. So that we have 2 times 1 cubed plus 1 divided by 3 times 1 squared minus 5. And then you'll get an answer and you plug it in again. You'll get an answer and you plug it in again. And I'll have the work for you here. Now, for the sake of not making this lecture too long, and also for the sake of you just not hearing me punching calculator buttons in the background, I'll have you try this on your own, but you'll see that these answers kind of start approaching that same point. Now let's use Newton's method in a different way. Now Newton's method helps us find a particular value or function. Now It works for zeros, but we can also be creative to find other points in our function. So question 2 reads, find the points at which the curves y equals cosine of x and y equals x intersect. So we want this particular point. That's what we want. But we're not too sure where that point falls. We see that it falls somewhere between 0 and 1. So to start off, pick a point, somewhere that's close to or within 0 and 1. You can try 0.5. So let's our initial point, our initial testing point be 0.5. Okay, so we now need to continue with our Newton's method. Now to find that point, we need to be clever using these two functions. Now, let me write this note. For our functions, so for them to intersect, the x-coordinate satisfy your two functions equal to one another. So g of x equals h of x, such that we result with g of x minus h of x equals 0. And that will be our new function. So that we have f of x is equal to g of x minus h of x equal to 0. So if we think of this as our function g, and we think of this as our function h, we just create their difference. So that we have this new function, f of x is equal to cosine of x minus x. Okay, let's go ahead and find the derivative. The derivative of cosine is negative sine. The derivative of x is 1. And again, I got these from these two functions, and we're trying to find where they intersect, so we set them as their difference. Okay, next in our step, we need to go ahead and find that formula, or create that formula. So from Newton's method, our formula comes from x sub n minus f of x n divided by f prime of x n. So we have all that set up. So we have xn minus our function, which is this, cosine of x minus x, and our derivative, negative sine of x minus 1. Okay, let's go ahead and simplify. Let's get this under the same denominator. And again, I make that same mistake of forgetting to write those little n subnotations. All right, once you clean it up, you're left with xn sine of xn plus cosine of xn divided by sine of xn plus 1. Okay, let's go ahead and start with our initial point. Now we said that we're going to start with this initial point of negative 5, right? We said that right there. Okay, so let's start with 0.5. Now we're going to use our calculator, so have it handy. We have 0.5 times sine of 0.5 plus cosine of 0.5 divided by sine of 0.5 plus 1. So pause the video, make sure you're getting these values in your calculator. 0.755222. Now we're going to repeat the process and plug in this new point. I'm running out of space, so we're going to plug in Now we're going to let x equal 0.755222. So that we have 0.755222 times sine of 0.75522 plus cosine of 0.75522 divided by sine of 0.75522 plus 1. And all that, let your calculator do that for sure. You should get something that's about 0.739142. You're going to repeat it until you start getting really close numbers. Now, again, for the sake of not making the video too long, I have these answers here. So our first one, we got 0.755222. Then we got 0.739142. And if you repeat it, repeat and repeat, we get something that's close to 0.739085. So 0.739 is a good answer. So we can say that our functions meet when x is equal to 0.739. All right, one more example. We can also use this to find extremums. Example 3, find the x-coordinate of the local extrema and the minima and local minima of the function f of x equals x to the 5th power minus 4x. Let me read that again. F of x equals x to the 5th power minus x to the 4th power plus x squared minus x on the interval from negative infinity to infinity. So we have a picture, and this picture is going to help us find an idea as to what we can pick. So, and again, there kind of isn't a right or wrong answer. You can start with anywhere, and by Newton's method, it will approach that value that is our solution. So we see here from our image that we have a local max and a local minimum. These max and minimums we see are from -1 to 0 if I had to make a very loose guess, and from 0 to 1. So I can pick any point within those boundaries or that are part of those boundaries to find these values. Okay, now to find our max and mins, if you recall from last section, from last chapter, chapter 4, these values occur at the derivative when our derivative is 0. So we need to make a slight adjustment to use Newton's method to find that local max and min. We need to work with our derivative as our function and actually find that second derivative. So let me write that down. When looking for the extrema, consider the derivative to be the original function. So our derivative, f prime of x, is 5x to the 4th power minus 4x cubed plus 2x minus 1. Think of that as your original function, and your derivative would be your second derivative. So that we have 20x to the 3rd power minus 12x squared plus 2, and that's it. Okay, so the first derivative is your original function, and the second derivative would take the place of the derivative. Now, again, recall your formula. xn minus, and then we have our original function, which is 5x to the fourth power minus 4x cubed plus 2x minus 1 divided by our derivative, which would be our second derivative. So 20x cubed minus 12x squared plus 2. And I keep forgetting those sub-n notations because they're not x's. We're manipulating our x's. Okay, and again, let's simplify. Now we multiply this top and bottom by our denominators and get that same denominator. So we have 20xn cubed minus 12xn squared plus 2. In the numerator, I have 20x, and I'm going to distribute in that xn. So to the fourth power minus 12xn to the third power plus 2xn, and distribute in that negative minus 5xn to the fourth plus 4xn cubed minus 2xn plus 1. Okay. So our simplified version of our formula would be 20 minus 5. We have 15. Xn to the fourth power. Negative 12 plus 4, we get negative 8. Negative 8, xn to the third power. No quadratics, and then the 2 and the 2 add to make 0. We're left with plus 1. In the denominator, we have 20 xn cubed minus 12 xn squared plus 2. All right, and this is our formula. We're going to go ahead and plug in values within our function to create and find that extremum, that max or that min. Now, you can pick negative 1 and 1, and it'll get you to that value. So let's go ahead and do that. Let's pick negative 1 and 1 to find these max points and low points of our function. So you go ahead and you start with x0 negative 1 and x sub 0 of 1 and work your way through it. Now again, for the sake of not making this video too repetitive and too long, well, longer than it is, I provided these answers for you. So if we plug in negative 1, we see that was that a min or a max? Let me take a look back at our picture. At negative 1, we have a max at negative 0.68335. So that's the x coordinate related to that maximum. And we have a minimum at 0.607. So we found those particular x values where your maximum and your minimum happen. That was section 4.8, Newton's method. Thank you.